Okay, so let's consider a different way of analyzing circuits. So far, we've considered the approach of equivalent resistance, and we've seen how that can be used to simplify some kind of complex circuits and solve the circuits. And what we mean by solving the circuits usually is after you construct a particular configuration of resistors and hook them up to a battery, and you want to know what the currents are through each resistor. That would be a typical kind of solution to a circuit that you would be trying to work through. If you have the currents going through the resistors, then you also have the potential differences also across the resistors as well. Now, sometimes complex circuits cannot be simplified using the equivalent resistance method. Okay, and that means that we have to use a different method, and we use what we call here Kirchhoff's rules. Okay, so we're going to introduce Kirchhoff's rules. I'll tell you first what the rules are, and then I will tell you how to use them, and then I will, most importantly, go through an example where we use the rules to solve the circuit. Okay, the first rule is a simple one. We've actually referred to it previously. If you have a junction, okay, so what do we mean by junction? I've also called that a branching point or a branch point. A junction would be something like this right here, okay, where you have a point where you have three or more pieces of wire that come to that point. So what that would mean in practice is if a current I is moving from left to right along this branch, it will break up, it will divide into two currents in the two other branches as it moves forward. Okay? And Kirchhoff's first rule simply says that the sum of all the currents that go into a junction is equal to the sum of all the currents that come out of the junction. Okay, so it's a nice, simple rule. And basically it's just saying that electric charge is conserved. So however much goes in, the same amount goes out in the same amount of time. Okay, that's what we're saying here with the first rule. The second rule is that the sum of all the potential differences across all elements, I mean a circuit element, across all elements around any closed circuit is equal to zero. Okay, I'll have to explain what that means by going through an example. Okay, but in mathematical terms, you could summarize it in this equation here. Well, I'm trying to get the whole thing highlighted. I can't. The sum of all the potential differences across all the circuit elements is equal to zero. If you go around a closed path, a closed loop, that means you end up where you started. So the potential difference at the beginning and the end are the same. That means if you cross a resistor or a battery or some combination of resistors and batteries that have potential differences across them, they all have to sum to be zero. Again, that's not going to be clear until I go through an example. But let's see, what can we do with this? Okay, so as I say down here in this line, an element means a circuit element. They can be either resistors or batteries, at least for the circuits that we are going to be considering. So let's consider a resistor between point A and B. If the current is flowing to the right from A to B, then that means delta V, which is defined as VB minus VA, the final minus the initial potential as you go across that resistor, that will be negative. How much? Well, negative I times R. Okay, so just think that current goes downhill in voltage. Okay, that's why going from A to B, delta V will be negative. Think of it as water flowing over a waterfall, right? The resistor is the waterfall. The current is the flow of the water in the waterfall. Waterfalls do not flow upwards, they flow downwards. Okay, so you're going downhill in potential, in electric potential, in the direction of the current. Okay, so if you go from A to B for the same resistor, but now the current is going from left to right, and I walk from A to B, well, I must be walking uphill in potential because current flows downhill and I'm walking against that direction. So as a result, the potential difference, delta V is VB minus VA, as we've defined it, will be positive. How much? Positive I times R. So when you go through circuit analysis using Kirchhoff's rules, make sure you keep this in mind for potential differences for resistors. The direction of the current matters. Okay, what about a battery? Well, current can flow through batteries. Surprisingly, they can flow in either direction through a battery. Now you might think, well, doesn't the battery want the current to flow from this short line to the big line, right? In other words, from the low potential to the high potential side of the battery? Yes, if that's the only battery. But sometimes there may be batteries pushing the current to flow against the direction you might think it does. In this picture, you might think the current is flowing from A to B because that's the direction the battery is pushing the current. But other batteries may be pushing harder and causing the current to flow in the other direction. Now, that doesn't matter for the potential difference, okay? For the potential difference, all you need to know is, unlike the case for the resistors, is that the electric potential depends on the orientation of the battery. So as I go from A to B, I'm going from the low potential, that's the short line, to the high potential, that's the big line, side of the battery. Okay, so from A to B tells us that VB minus VA, which is delta V, is going to be positive. How much? Well, whatever the EMF of the battery is, neglecting internal resistance. If I turn the battery around, again, it doesn't matter for batteries what direction the current is flowing. If I turn the battery around and I go from A to B, I'm going from the high potential to the low potential side of the battery. So the potential difference must decrease. How much? Well, whatever the EMF of the battery is. So it's minus E if we neglect the internal resistance of the battery, which we usually do. Okay, so what are we going to do? We're going to use these rules to solve problems dealing with electric circuits. Here are a list of problem-solving hints. Again, it won't make much sense until you start going through a specific example. Okay? We'll go through 2 examples. Let me just go through these points really quickly. So in a typical problem, you're given a circuit with batteries, often more than one battery, and resistors, R's, and you want to find the currents through every single branch of the circuit, through every resistor, and maybe through every battery. What you're going to do is you're going to label each unique current, and there will be one for each branch. You often have no idea what direction the current is flowing in any given branch. So what you do is you make a guess. Okay? And you might think, well, what if I guess wrong? Well, if you guess wrong, that's fine. All it will mean is your solution for the current will come out to be negative. Negative means the following. If you guessed the current was flowing from left to right, and then the current comes out to be a negative number, then it actually means the current is flowing from well, what did I say? Just the opposite direction. If you guess from left to right, it's actually flowing from right to left, with the same however many amps of current that you have guessed, or so that you have calculated. Okay, once you've done this, you can apply Kirchhoff's rules. I call them laws here. Sometimes they're called laws. Really, they're rules for different nodes and complete loops in the circuit. If you have n different branches with n unique currents, you need n equations to solve for the currents. We'll see what this means shortly. Okay, so here's one of the simplest examples. And what do we have? we have, oh, it's just a single loop. It's just a single loop. Okay? So, and what do we have? We have 2 batteries and 2 resistors. Now, I want you to notice that the batteries are oriented so that one battery is trying to drive a current in one direction. The 6-volt battery is trying to drive a current that goes clockwise, right, out of the high potential terminal and around and back into the low potential terminal. This 12-volt battery is trying to do the opposite. It's pushing in this direction, out of the high potential terminal, counterclockwise, and into the low potential terminal. Okay? So, question is, which battery wins? What direction is the current actually flowing? In this case, you could probably guess the 12-volt battery is going to win. But let's say we don't know that. I'm going to guess that the current flows clockwise. So, for example, from between point B and point C, the current flows from left to right across this 8 ohm resistor. Down here, that would mean the current is flowing from right to left. Okay, so let's use one of the rules of Kirchhoff, namely the second one, the voltage rule, to calculate the current. How do we do it? Okay, let's consider this loop I can't highlight that alone. A, B, C, D, A. So I'm going to walk from A to B to C to D and back to A. Okay, clockwise around. Now this has nothing to do with the direction of the current necessarily. It's just you can take a walk around a loop in any direction you want, and clockwise or counterclockwise. And all you need to know is that the sum of the potential differences across all the circuit elements must be equal to 0. So let's go. Let's do this. So I start from A and I walk in the direction to B. And what happens? I walk across this battery. And I go from the low potential to the high potential side. Short line, long line. Okay, so that means the potential is going to increase. How much? Well, whatever E1 is. So I write down positive E1 here. And that's going to be 6 volts. Next, I continue my walk. I'm choosing to walk clockwise. I walk from A to B. And what happens? I cross a resistor. Therefore, the potential is going to change as we go across the resistor. Will it be positive or negative? Well, let's remember what we said up here. Okay? If we go with the current, then we're walking downhill in potential. The potential, delta V, will be negative. Negative I times R. Okay? So, because I'm walking with the current here, I know the potential difference has a magnitude of I times the resistance R1, and I know it's negative because I'm going from the high potential side to the low potential side. How do I know that? Because the current is flowing to the right and the current flows downhill. Now wait, what if the current is actually flowing in the other direction? Well, then we will find out at the end, because the current will come out to be a negative number. Okay? So next I go from C to D, and I notice I'm walking downhill in potential. So I go negative E2 here. Negative E2 will be negative 12 volts. And continuing, finally, going from D to A, I'm walking across a resistor. I know there will be a potential difference of either positive or negative I times R2. But here I know it's going to be negative, assuming we've guessed the direction of the current properly. Okay, because we're going with the current goes downhill, the potential decreases. So it's negative I times R2. The sum of these potential differences is equal to 0. I solve for the one unknown I have, which is current, and out comes, so you plug in these numbers, out comes a negative current.